Shalom, my name is Or and I want to present to you our work on plug-and-play task-level autonomy for robotics. Motivation. There is an increasingly wide range of available robot skills. These skills are usually scheduled into effective behaviors using handwritten scripts. These scripts are non-optimal and hard to maintain upon environment change or robotic skill upgrade. AI planning is a possible alternative for controlling the robot. Nevertheless, AI planning requires AI expert and a significant integration effort caused by the abstraction gap between low-level robot code and decision-making models used for AI planning. Moreover, robotic engineers are unfamiliar with action description languages used for AI planning. And finally, the current action description languages are not expressive enough for real-world robotic domains. Our goal is to provide a plug-and-play task-level autonomy for robotics. Our solution is the Autonomous Operating System, the AOS. Our conceptual contributions are that this is the first integration framework that supports full POMDP models, which means stochastic actions, partial information, and noisy sensing. These are essential for robotic domains. It also offers a code-based skill description instead of logic-based existing action description languages. Programmers do not need to learn new language. It harnesses the rich expressiveness and execution advantages of a programming language. And we also provide a novel, explicit and principal mapping between the more abstract skill model and skill code, mapping from high-level skill parameters to code parameters, mappings from code variable and return value to observations needed for decision making. Our engineering contribution is a true plug-and-play system. Given a model of the skill code, the environment, and the goal, no additional programming effort is required. In here, we see the documentation is all you need. These are the files needed to integrate code with our system. There is one environment file documentation for the possible state variables, the initial state, and the goals of the robot. And for each of the possible skills, you need to document the skill documentation, which contains the skill effects, skill costs, and the observation model, and also an abstraction mapping on how to actually activate the code. And it can define also variables based on robot low-level published data, and these variables can be used to map low-level code execution to observation needed for decision making. In this example, we can see for our gazebo armadillo robot that we have 4 different skills, and for all of them we gave SD and AM documentations. And in here we can see that everything is working, yet the robot mistakenly thinks it is holding the cup. It happens because a successful response is sent from the code when the arm trajectory to pick the cup is successfully calculated and executed, which does not guarantee it holds the cup. Nevertheless, the AOS knows from the documentation that the peak observations are noisy, so it tries the second cup since it may drop the first one, as we can see. How can we improve the robot performance by only changing the documentation? The AOS offers ways to improve robot performance without changing the skill code. An easy one is to improve the peak observation accuracy by adjusting the peak skill AM documentation. The AOS listens to public data published in the robot framework and not only from the executing skill, which we can listen to the robot finger opening level posted by the arm driver and know if the arm is actually holding something when the peak ends, so we can make the observation more accurate. All we had to change is just to add the local variable for listening to the arm gripper, to define its source, and to say the threshold, as we can see in the top frame. And we needed to change the response rule for the observation when executing the skill, so we just need to consider that we not only listen to the peak response success, but we added also to listen to the additional local variable, saying if the can is actually holding something after the peak execution. In here we can see a tic-tac-toe example we implemented with our Panda cobot. We implemented two basic skills, one that the robot can draw a circle in each of the grid cells, and the other one that it can detect board state changes. We documented the two, and we also documented the environment file with the robot calls, and we can see that the robot is acting as expected. We can also see that one can easily emulate an arm with a difficulty drawing in the center square. All we had to change is just to say that it is successful in case that it is called to draw in the center cell after we sample from a Bernoulli distribution of 0.5, and only then it really marks the cell. This is used, of course, for planning. When execution occurs, if it succeeds or not, it depends on the robot, but now we can document it easily. Thank you very much for listening.